Hey everyone, this is our last little lesson that we have for piecewise functions in our Unit 11, the last unit of our year. Yay! All right, so as we go through, one of the main things that we need to know is actually the definition of a piecewise function. And a piecewise function is made up of two or more different functions. So in the example that we have graphed to the right, I'm going to kind of talk about a couple of sections of it. So if you'll notice the farthest section over here on the left-hand side that kind of curves down and comes back up, that is a portion of a quadratic function, like y equals x squared, something like that. And it does have a particular domain, and that's the other part to our piecewise function. Each portion of the function has its own particular domain. So for this particular function, the x squared part, it is only drawn from negative infinity up to x equaling 1. So, and that said, its particular domain would be if the x's are less than or equal to 1. And the reason I got to use the equal to bar is because there is a closed circle right here at the point 1, 1 on that particular function. When we look at the next little section, we have just this teeny tiny little line segment, and that's drawn between 1 and 2. Anytime you just have a number, that is a horizontal line, so it's just y equals that value, and its particular domain starts at positive 1 and ends at positive 2. Since there is an open circle at the 1, I'm just going to do a less than x. Since there's a closed circle at the 2, I'm going to do less than or equal to 2. So that's saying that I'm going to draw y equals 3 only between positive 1 and positive 2. And the last little section of our function that we have starts at x equaling 2 and travels all the way out to positive infinity as it increases to the right, and it does begin at x equaling 2, but it doesn't actually equal that value because it's got the open circle. So that function could be something along the lines of y equals just positive x, just a linear function, and its domain is going to be when all the x's are greater than 2. And again, that's because it has an open circle. So as we go through our piecewise functions and we actually look at the graphs, we are going to get each section drawn for its particular domain. Our first part, though, of our piecewise functions is actually to evaluate our piecewise functions. And what that means is that what we're trying to do is we just want to create an XY table so we would know where the points are to plot on our graph. So for our first one, f of x equals these two pieces, x squared minus 1 when the x's are less than negative 2, and then we'll draw 5x plus 3 when the x's are greater than or equal to negative 2. So you can kind of think on a number line, negative 2 is my boundary. I'm going to graph one function to the side, to the right, so this would be the 5x plus 3 function to the right, and then the x squared minus 1 function is going to be drawn to the left. So if I'm looking at any values that are less than negative 2, this right here, I'm going to use x squared minus 1 to evaluate. So our first one, f of negative 5. In that case, x is represented by negative 5, and negative 5 is less than negative 2. So we're going to evaluate f of negative 5 in the x squared minus 1 portion of the function. So I'm going to substitute in negative 5 for the x, square it, and then subtract 1. Negative 5 squared would give us positive 25, and 25 minus 1 does equal 24. So again, basically what we've done is if we were to type that function into the calculator and look at the table, when x equals negative 5, your y value is what you're solving for. That's what it should be. It should be 24. Okay, our next example we got to be a little bit careful with because this says f of negative 2. And both of these inequalities, both portions have a negative 2. But I need to use the one where it says equal to negative 2. So this is when x equals negative 2, what is the y value? Okay, in that case, f of negative 2 is used in the portion that's 5x plus 3, that linear part. So I'm going to substitute a negative 2 for the x, multiply by 5 to give us negative 10, and then add 3. So we'll determine that f of negative 2 equals negative 7. Again, a table for that particular function. If I substitute a negative 2 for x, or I look down the table as my list, I should see the y value equaling negative 7. And our last example, f of negative 7. So I'm looking when x equals positive 7. Excuse me, guys. Mistake. Positive 7. Positive 7 is definitely over here to the right-hand side. So we're going to use that same part of the function again, the 5x plus 3. And we are going to substitute 7 for the x, multiply by 5 to get 35, and then add 3 to get 38. So when my x value is positive 7, my y value is 38. There you go. We'll practice another one of these, and then we'll jump into actually graphing our absolute value functions. Our piecewise functions. We've already graphed absolute value. Okay, example 2, you'll notice this one has 3 different sections. So if it helps you to break it out on a number line, kind of look to see where all of those spots are. Our first portion, g of x equals 1/2 x plus 3, when the x's are less than or equal to negative 4. 1/2 x plus 3 is going to go to the left of that value. And I would put a closed circle if I was thinking about it. We are also going to graph negative x minus 1 when negative 4 is less than x, which is less than 1. So between negative 4 and positive 1, I would graph the function negative x minus 1. It's only drawn in that little section. It has a very specific domain. And the last part of our function is 2x cubed plus 9 when x values are greater than or equal to 1. So when I'm greater than or equal to 1 going to the right, I'm going to use the function 2x cubed plus 9. All right, so let's check all of our values and see which ones we'll use. G of 2, okay, is 2 less than or equal to negative 4, between negative 4 and 1, or greater than or equal to 1. 2 is definitely greater than or equal to 1, so we are going to use the 2x cubed plus 9 function. Okay, so to evaluate, we're going to do what we did in the last examples. When the x value is 2, we'll say 2 multiplied by, whoopsies, I was doing my power first, excuse me. So 2x cubed plus 9, so it's 2 multiplied by 2 to the third power plus 9. Remember, you got to do your exponents first. 2 cubed is 8. 2 times 8 is 16. And 16 plus 9 gives us 25. So g, evaluated at 2, has a y value of 25. There you go. Okay, our next example, g of negative 1. Okay, so where does negative 1 fall? Does negative 1 fall greater than or equal to 1? No. Is it between negative 4 and positive 1? So is negative 1 over here? Yes, it sure is. So we are going to use that middle function, the negative x minus 1. So g of negative 1 is a negative times the x, which is negative 1 minus 1. Negative 1 multiplied by negative 1 gives us positive 1. Then we'll subtract 1. So we'll simplify to get g of negative 1 having a value of 0. Again, in the table, if our x is negative 1, our y value is 0. And last but not least, g of negative 6. Negative 6 is definitely less than or equal to negative 4, so we will use the function 1/2 x plus 3 to evaluate. We'll use that portion of it. So g of negative 6 equals 1/2 multiplied by 6 plus 3. Oops, excuse me, negative 6, I forgot my negative. Half of negative 6 equals negative 3. And negative 3 plus 3 does give us 0. So when we substitute a negative 6 into the equation, we get a y value of 0. And there you go. That is evaluating our piecewise functions. I'm going to show you how to graph one of the piecewise functions. We have several in our examples, and then I'm going to stop the video so that you just see one and that you can kind of practice and look through. We're only going to do 15 minutes at a time, and then I'll come back and show you the rest of them in a second video. All right, so our first piecewise function to graph, f of x equals x when the x's are less than or equal to -3, and it equals -2x plus 1 when the x's are greater than 3. All right, now something that I do purely for a visual is I look to see what value splits my domain. Okay, so in this case I've got one function to the left of the -3 and one function to the right of the -3. So I just visually, very lightly draw myself. It's kind of like an asymptote. It's not. It's just a boundary line so I know which function goes where so that I don't goof them up. So I'm going to graph x when the x values are less than or equal to -3. That one's going to go on the left. And we'll make a table for that and get that rolling in just a moment. And then I'm going to graph -2x plus 1 on the right hand side when all of the x values are greater than -3. Now the kicker with this is, for each of these you do have to actually use -3 in both of your tables. Okay, so use your calculator and type in your table y equals x, and then in this case for my x values I want to start at -3. And then I want to choose numbers smaller than that because it says less than. So then I'll scroll until I see -4 and -5. You could even write down -6. And when you look at those points, when x is -3, your y value is also -3. When x is -4, your y is -4. When x is -5, so is the y. And when x is -6, your y value is also -6. Okay, so when x equals -3, my y value is also -3. All right, what I want you to do is put your point there, but then look to see if I have a less than or equal to bar, that means that we have a closed or a filled in circle at that first point. And I just kind of give myself those little notes as I go through to help me remember little stuff like little pieces like that. And then I want -4, -4, -5, -5, -6, -6. And there's my red graph to the left-hand side of that little imaginary boundary line that we have. All right, we are now going to graph our next function. So in your table, you're going to type in, -2x plus 1. And again, I do want to use the x value -3 because I'm using that one, but then I have to go greater than that. So I could do -2, -1, and 0. Just pick a few of them. Before we get going, make note that we can graph -2x plus 1 when x is greater than -3. So this is an open circle. That means the very first point on that little boundary line that I kind of drew, that's got to be open. Okay, now look at your table. When x equals -3, you should have a y value of +7. So at -3, +7, you should have an open circle. At -2, you should have a y value of 5. So -2, 5. At -1, you should have a y value of 3. And then at 0, you should have a y value of 1. And then we will have this line drawn to the right going down. Okay, now take a moment, kind of look at your stuff and make sure you've got it down pat. And I hope you recognize that both of these are linear functions. The first one, x, has a positive slope, so the left side of the graph is actually increasing as we move to the right. And the second one does have a negative slope, so that one is decreasing as we move to the right. Okay, our domain. Look from left to right. We're definitely starting at -infinity. I do see a break in my graph. There is a big, huge break. Okay, so when x equals that -3 value, it totally messes up my function because I've got one solid point and one open. So one closed and one open. That means that our function, and I want to make sure I write this real nice for you guys. So x equaling -1 is a point of discontinuity. It's where the graph is discontinuous, and that means your graph is just jumping and starting something else. Okay, so you can also say discontinuous. It's still included because I get x equaling -3 for the red, but it doesn't equal it for the blue. Okay, so it is included. So if you're looking at your domain and you go, hey, Miss Fairbanks, it works from -infinity to -3 with a bracket, and then it picks up again on the other side of the -3 with a parentheses because it's not open and goes out to infinity, that's true. But because one side includes it, this side right here on the left includes it, that means that really and truly the entire domain is -infinity to infinity. They mean the same thing. Totally get that you would write it split up. Okay, your range goes from bottom to top. The red graph points forever and ever down to -infinity, as does the blue. They continue both to -infinity. As we increase up, the red one does stop, but the blue one is still continuing in a positive direction past y equaling -3. However, the blue graph stops at +7 and it does not go any further, so this is the maximum y value that you have. Y equals, or y is less than 7. All right, so quick recap. We have two pieces of the function. In this case, there's one x value, x equals -3, that is discontinuous. One part of the graph is drawn up to and includes that value. The other part is drawn away from and does not include that value. Okay, your domain goes from left to right, -infinity to +infinity, even with that point of discontinuity. And your range goes from bottom to top. It does not include the 7 because that particular point is not a closed circle. All right, so that's it for this first video. Went a tad over, but we're close to 15 minutes, so we should be good. Be back in a little bit with the next video to continue on this topic.